All right, I'm going to go ahead and get started with the introductions for the webinar. Thank you so much to everyone joining us today, and thank you for our panel for putting the time in today to answer everyone's questions. So today's webinar is an Ask the Experts webinar, meaning we have an expert panel here today who will be fielding your questions live. Our topic for today is water and mining implementation of slope depressurization programs. And this webinar will run for 90 minutes, so from now until 9:30 a.m. or until we run out of questions. So this webinar is brought to you by the Geotechnical Center of Excellence at the University of Arizona here in Tucson. We are industry funded and member led, and we are an interdisciplinary center who collaborates on research and educational projects in the geotechnical realm with the goal of bridging gaps within and between academia, industry, and fields of study. And if you'd like to know more about the GCE, feel free to reach out to us. We'd love to talk to anyone that wants to know more. And then the topics that we're talking about today are related to one of the GCE's professional development courses, which is the Water in Mine Operations and Slope Stability course. It is currently available through our learning portal, and it covers all the topics you see here today. You can either scan the code here if you want to learn more about the water course, or one of my webinar teammates will be posting in the chat some more information about the GCE courses. And that course is developed in partnership with Pitot Associates, who we have some representatives here from today on our expert panel, and also the Large Open Pit project provided funding for the underwriting of that course. And then the GCE, as a member-led and member-funded organization, we must say thank you as well to all of our great member companies who support the GCE and all the work that we do. So you see them here on our screen. Thank you very much to all of our members. We really appreciate you and your support. And now to introduce who's here today. We have our webinar team from the GCE, which includes myself. I am Jillian Noonan, Senior R&D Engineer with the GCE. We have James McNabb, who also is Senior R&D Engineer with the GCE. James, thanks for being here this morning.
Thank you. Good morning, everybody.
As well from the GCE is Benjamin Meyer, and Benjamin is R&D Software Engineer, who will be also supporting the webinar today. Thanks, Benjamin.
Thanks, Jillian, and thank you everyone for joining us today.
And now it is my pleasure to introduce our expert panel. Today on the panel, we have Jeff Beal. Jeff is Global Technical Advisor with Pitot Associates, as well as one of the lead technical advisors for the water course and a presenter in that course. Jeff, great to have you today. Thank you.
Thank you, Jillian. I hope we have some good discussions.
As well, we have Jeremy Dowling. Jeremy is Hydrogeology Advisor and President of Pitot Associates, as well is a lead technical advisor for our water course and a main presenter. Jeremy, very great to have your expertise here today. Thank you.
Yeah. Hi, everyone. Nice to be here.
And then also joining us is Travis White. Travis is Principal Hydrogeologist with Anglo American and is also a presenter in our water course. Travis, thanks for being here.
Thanks very much, Jill, and hi to everyone. Looking forward to the discussion.
And we have Simon Scholl. Simon is Principal Hydrogeologist with Pitot Associates and a presenter in our water course. Thanks, Simon. Great to have you always on our panels.
Thanks, Jill. Hey, everybody. Looking forward to it.
And then we have Lauren Lorick. Lauren is Principal Consultant with Itasca Consulting. And Lauren is a presenter in some of our courses, not the water course, but is an expert in many things related to geotech, hydrology, and mining in general. So Lauren, thanks for being here. Glad to have you on our panel.
Hi, everybody.
Okay, now I'll go through just a few tips for our live participants that are here in this webinar. So we encourage you to interact throughout the webinar with our panel by asking questions as we go through. We'll be accepting questions all throughout the webinar. To start off, just housekeeping, you are muted, your video is off, considering this is a webinar. If you have a question, we have two different ways to communicate in the Zoom. You have a chat, and then you also have a Q&A, two different buttons on your control panel. So the chat, you can just use, some of you have used already to say hello to us, just general chatting, but we would like you to put all of your questions through the Q&A function. If you click on Q&A, it will open up a window where you're able to type your question in. You will be able to see others' questions. If you see a question that you particularly like and would like our panel to address that as a higher priority, you can give it a thumbs up and we will see that. And just noting that we're recording this webinar, so we'll be posting it to our watercourse site as well as the GCE's YouTube page. On the YouTube, we do have a history of some of our past webinars. So if you have missed any of the previous webinars, this is the fourth in the water series for this year. You can go back and watch those on our YouTube or on the course site if you're in the course. And there's just a quick note here that the webinar content that is included today is intended for educational purposes only and is not meant to replace a direct consultation with an expert in the topic of your concern. So thanks for joining us today. And with all that, I will introduce now the topics we'll be talking about today. So as I mentioned, this is the fourth webinar in a series of water and mining focused webinar topics that we've been running through this year. Today is implementation of slope depressurization programs, but based on the content in the water course, that can include topics beyond just slope depressurization. And we can discuss today strategic planning, surface water management, in-pit real estate and access, and just general site-wide water management. So we will be accepting questions through all of those topics today. And our presenters are all experts in those topics, as far as I know. So at any time, you can start entering your questions. What we'll do is go through some pre-submitted questions, and then you can start now. I'll invite you to open your Q&A and enter any questions you might have, or questions as we go along as follow-ups to the pre-submitted questions or any other questions you have prepared. All right, panel. I will be reading out each question, and then I will open it up to the panel to discuss. So the first question came in through the GCE's email and is on just a general understanding of the terms dewatering versus depressurization. Are they one and the same? For example, isn't dewatering creating depressurization for the materials by removing pore pressure? And isn't depressurization achieved by removing water or dewatering? So could you please clarify the difference of these terms? Thank you. So I'll open that up to the panel. If there's anyone that would like to start on this question, please go ahead. And we've lost your audio, Jeff, after we checked and checked.
Oh, can you hear me?
Yeah, go ahead, Jeremy. You
Yeah,
sound
okay, I'll talk about
clear.
it for a couple of minutes. So there's a lot of overlap between dewatering and depressurization, but we try and distinguish the difference between situations where we have to deal with very large volumes of water inflow to the mine, which may be disruptive to actual mining operations, from pore pressure in the pit slopes that may be detrimental to slope stability and the geotechnical performance of the slopes. So with depressurization, there are many examples of where there's actually very little water flow involved. The rock mass may be very poorly permeable or highly compartmentalized, so there's little or no need for the mining operation to deal with dewatering or the removal of large volumes of water. But nonetheless, there is still a need to depressurize the pit slopes. In other words, remove the pore pressure and the hydraulic head in the rock mass and the structures in order to create an adequate factor of safety and a stable slope for geotechnical purposes. So dewatering generally involves production pumping of large volumes of water, and it could include sump pumping or large diameter production wells to remove large volumes of flow from the groundwater system and from the mining operations. Whereas depressurization would typically involve more targeted and focused drainage measures, such as horizontal drains or drilling drains from underground drainage galleries in order to remove the pore pressure from the rock. So that's really the distinction between dewatering and depressurization. But it's also true that if we are doing a dewatering operation, we would expect the removal of the water and the lowering of the water table to have a beneficial impact on the pore pressures in the pit slope. So if we're undertaking a dewatering program, there's always some overlap and some benefit gained with controlling the pore pressures in the pit slope.
Have I got my audio back?
Yeah, you do. So I was just going to add one wrinkle to this. Agree with what Jeremy said, and dewatering, depressurization normally are associated with water in the rock or soil mass. I had a boss who told me that when you pump out from a sump, then that was not water inside the rock or soil, that was termed unwatering. I don't see that anyplace else. Maybe that was just his term, but it's probably useful to have a separate category for that as well. And if you want to use it, go ahead.
Yeah, it might be interesting if anyone has any other terms they use, put those in the chat.
I don't think, I mean, dewatering is a pretty universal term. I think, you can't depressurize without first dewatering. But you can dewater and still leave pressure in low permeability rock.
Makes sense.
Possibly related to Lauren's unwatering comment, I was going to throw surface water in there. Some pumping out of some pits in some locations, the surface water rainfall component of pumping is considerably bigger than any kind of groundwater component to the pit. But rainfall can also cause elevated pore pressures, transient pore pressures. So, as Jeremy said, the two are very well connected. And being able to understand how your water moving through the system, be it groundwater or rainfall, surface water, shallow infiltration, whatever terms you want to use, understanding how that water moves is important for both dewatering and depressurization. So there's certainly links, but they also have two very different purposes.
All right, good. I think that we've made that really nice and clear. Any other final comments from the panel?
No, I think we killed it.
All right, and I do see some people starting to ask questions in the Q&A. We will get to those in just a moment. Thanks for entering your questions, and keep doing that throughout the webinar. So our next question is in from Isabel and asks, I understand that a goal for drilling a dewatering well is to intersect the largest fractures for great yield, or the A fractures, as described in the course. Can you discuss tips for fracture characterization to increase the likelihood of hitting these fractures? And how can you best verify during drilling or dewatering? I'm assuming that you have hit those fractures. So I'll open that up to our panel.
Okay, I'll take a first go at it. I think just to a comment on the first bit of the question is, yes, the goal of a dewatering well is to intersect the largest fractures for the greatest yield. But the other thing to consider is those fractures need to be at the correct depth. So if you intersect fractures too shallow, for instance, if your pit is 500 meters and you hit fractures at 200 meters, then the longevity of the well isn't going to be very sustained. So the deeper, given that dewatering inherently creates a drop in water level and therefore inherently creates a reduction in well yield, the deeper you can intersect the fracture, the more efficient your well, the more sustained your pumping rate. So that's just something to think about as the first part of the question. And really, for the second part, there's no substitute for drilling a pilot hole, particularly if you're going to have to spend a lot of money on a production well. So you can look at the fractures from core, you can look at the fracture orientations from core logging, from the general understanding of the site, but there's no substitute for drilling a pilot hole and testing the fractures that you encounter. And so, most fractures are highly variable, as is stressed in the course, and you can have a fracture with or a fault zone with a yield at one location, and you move 20 feet away, and that same fracture or fault zone may not produce anything. The fractures may be healed, the fault may be pinched. So really, there's no substitute if you're going to spend significant amount of money on a production well. There's no substitute for advanced drilling to characterize the fractures. Particularly where you've got an initial site investigation where you don't understand the fractures. Once you know the site and you have a little bit more confidence that the fractures are homogeneous or they're consistent, then you can maybe drop the pilot holes. But there's an example I had from several years ago of a site which was putting in wells which were about $3 million each, and they just got consistent fractures every time, so they dropped the idea of a pilot hole, and then lo and behold, they drilled a dry well because they hadn't put a pilot hole in it. So really, there's no substitute for pilot hole drilling.
Any other comments? I see, Travis, you have your hand up.
Yeah, thanks, Jill. Look, fully agree with everything Jeff has just said. But maybe just one step back, when you're dealing with fractured aquifers, you really need to understand the structural model for the site. So the structural model is going to give you sort of a desktop view of where your high potential areas are. And then you can always go and, zoom in and get better resolution on particular targets with, on-site field-based geophysics. So we've done it quite successfully at a number of our sites using things like suborder magnetics. It's going to depend, from site to site, but suborder magnetics has worked really well. This is particularly difficult when you've got vertical or near vertical structures, right? And especially if you're drilling through some overburden. So it's good practice to spend a bit of money on some of the ground truthing on the geophysics, just to get the orientation in terms of which direction is the structure dipping, so that, to link up back to what Jeff said, so that you can hit the structure at the right depth. We've had cases where we've moved holes, a couple of meters, and they've been dry. So it's really important that you drill that pilot hole and you understand the orientation of the structure that you've hit with the pilot hole, so that when you drill the production well, that you move it in a long strike, with the structure that you've hit. The second part of the question, how best can you verify during drilling? If you're drilling, normal DTH percussion, you'll see the drill chip size will be coarser, or no drill chips will come out when you hit a big fracture. Hopefully you would have hit some water, so you'll get, maybe before you hit the water, you might start getting a little bit of air loss, and then you'll hit the structure, and then you get water returns on surface. But the drill chips normally indicate, you know, a little bit in advance of the structure. And depending on what geology you're drilling through, there are some sort of indicator minerals that will show signs of water. You know, like your iron carbonates, calcites, things like that. Especially in your karstic aquifers, you get, you know, those carbonate minerals that will precipitate out, and you'll get them coming up in the drill chips.
Thanks,
David,
Charlie.
I'll just add a couple of comments as well. So when along the lines of what Jeff was discussing about pilot holes, so if you drill the pilot holes with air, you can log the flow rate coming out of the hole all the time during drilling, and you can see kicks in the flow rate or changes in the flow rate as you drill, which usually correlate to the locations of the fractures. And then when you've completed the pilot hole drilling, you can do a prolonged airlift test. So you just pull the drill string off the bottom of the hole and circulate air for a prolonged period. And the sustainability of the flow coming from the hole gives you an indication of the broader fracture network. And if the flow rate is sustained, it can indicate that the location is interconnected to a broader fracture network that may sustain a good pumping well. Whereas if the flow rate rapidly decreases, maybe the fractures are very localized, and a pumping well would be less sustainable at the location. So there's a lot of different practical testing that can be done during the drilling of the pilot hole to try and understand the location of the fractures and how interconnected and productive they may be if you proceed with drilling and constructing a pumping well at the same location. And then the other thing is just talking about Travis's points about using the structural geology map. So the other thing that can be done is once you have a good library of pilot hole data across the site, is you can take all the pilot hole data, so all the pilot hole logs and the locations of where the productive fractures were encountered in all the pilot holes, and you can just map that into the geology and the structural model of the site in a program like Leapfrog. And then you can start to try and correlate the occurrence of the fractures with the different types of lithologies and alterations and major structures, and get an understanding of what the geological controls are on the more productive fractures. And then you can use that information to start trying to help more accurately predict where the good zones are in the ore deposit to target for dewatering well drilling.
All right, thanks, Jeremy. We do have a follow-up question related to this question that came in from the live participants that I'll pull up here on the screen to continue the conversation. Grab it. Just making sure that we cover this question as well. So possibly we talked about this a little bit already, but what is the best method to characterize these kind of fractures? Specifically, is the fault kinematic analysis important to characterize the fault system?
So I think we've said that, you know, the best method is to drill a hole and test the hydraulics. Yes, the fault kinematics is useful, but fractures and faults, their hydraulic characteristics vary over short distances. So essentially, there's no substitute for drilling a hole and actually running hydraulic tests.
Good. All right, thank you, Arsene, for the question. Okay. Any other comments before we move on to a slightly different topic, perhaps? I'm going to pull up another live question. So this question is from Raymond, and Raymond is asking, how do we determine if we should use either a standpipe piezo or a vibrating wire piezometer? Any thoughts from the panel? Travis, looks like you have your hand up. Would you like to start?
Yeah, thanks, Jill. This is actually a really good question. And we've had we've battled with this on a few sites. So look, in general, the rule of thumb, or maybe let me start with a standpipe piezo first, what it is, right? So standpipe piezo by definition is an open hole with either fully perforated or perforated at particular horizons, and you get a composite water level. All right. So all the various water bearing units are able to water is allowed to flow through the casing into the bore. Then your VWP, your vibrating wireline piezo, is generally grouted in and typically multi-level. So you've got a sensor, pressure transducer, grouted in at specific horizons that you're trying to measure pore pressure or phreatic surface. Okay, so you can use a VWP in an open standpipe, right? It does the same job as what a level logger does. We use them as almost standard practice now because they're slightly cheaper than the level loggers, and it integrates with the grouted VWP network that we have. So how do you determine whether you need a standpipe piezo or grouted VWP? In unsaturated environments, so typically your shallow, alluvials or shallow aquifers that are unsaturated or perched, you can get away with an open standpipe because you're measuring, it's saturated below a certain level, and you won't pick up any difference in pore pressure if you had grouted VWPs. And typically in sort of monolithologies, one geological unit or lithology. As soon as you go to multi lithologies, different levels, or deeper than say 50 to 100 meters, then you might want to switch to VWPs, at least initially. All right, so you can characterize and determine whether there is a difference between the pore pressure or phreatic surface at different elevations or different depths. I can give you one example of a site where we had a combination of open standpipes and VWPs, and what we ended up doing is this particular site had some clays in their slopes, so there we went with grouted VWPs on the upper slopes, and the deeper aquifer, which is a fractured rock aquifer, we put in multi-level VWPs, and we confirmed that all the different horizons showed essentially the same water table, same phreatic surface, same pore pressure. So then it's not necessary to have discrete VWPs. It also was pretty costly and quite a nuisance to manage. So we had in the fractured aquifer open standpipes, in the upper slopes where we had the clays and other lithologies, grouted multi-level VWPs. So horses for courses, really, but that in general, that would be the approach.
Yeah, I think iron ore is a good example, Travis. That in a typical banded iron formation, you don't get a lot, or in many banded iron formations, you don't get a lot of vertical head difference, and so standpipes for general dewatering of iron formations are often adequate. But the sides of the pit where you've got phyllites or clays or weathered quartzites, and the water holes up in those, then the standpipes aren't much use for characterizing the pore pressure. So you need a combination of standpipes for the quote unquote aquifer unit and VWPs for the lower permeability or the compartmentalized units in the pit wall, which hold up the pressure. The other thing, as you'll get from the course, the other thing to think about is, I always say get as many water levels for a site as you can. And whenever I go to a new site, I never look at the permeability data. The first thing I look at is the water levels. And if the water levels are all similar, I know the system's connected. If the water levels are all different, I know you've got discontinuous flow. So get as many water levels as possible in the early stages of a project, when you just drilling exploration holes and when the project's still at concept level or in an early stage. Just get as many water levels as you can, and put in standpipes in open holes, or just measure water levels in open holes. the more water level data you can get, the better you'll understand the site.
All right, thank you for that discussion. Travis,
sorry.
if you could go ahead, Simon.
Sorry, Jill.
Yeah, go ahead. I was going to ask if anyone had any additional comments, so please go ahead.
Yeah, no, I agree with everything Travis was saying and Jeff, but I was just going to throw in a sort of quality of installation as well. You know, if you are just looking for water levels, just take a measurement in an exploration hole if you want to. But if you're installing VWPs, you've got to install them properly. As you know, they're not particularly expensive, but they're not cheap if you're putting in a deep installation and grouting it up using some drillers or a rig or something to do it. And so just do a good job, because it's worthless data if you don't do it properly. So if you can't install VWPs properly, well, then maybe a standpipe piezo is better, as long as you can make sure you do it properly.
Yeah, I think the key point is whatever data you have to interpret it. And if you have a standpipe, as Travis says, it's open to several different horizons, obviously. So it's the more permeable horizon that gives you the dominant head in the standpipe.
Yeah, and I was just going to add, VWPs are particularly useful and relevant when you've got a low hydraulic conductivity or compartmentalization. That's when they really they really show their value. When you've got these sort of highly fractured, high K, high flow environments, open standpipes do a good job. But even then, I would still, at least go through the effort of installing 1 or 2 multi-level VWPs there, just to pinpoint, or confirm rather that your composite water level that you're getting from your open standpipe is representative. Just last comment, Jill, on the deep multi-level installations we did do on one of the at one of the sites that high K, high flow, highly fractured. What was really useful was the regional recharge we picked up a lag. So it was the underlying dolomites were the sort of the regional aquifer that was feeding the mine. And we picked up there was sort of a 3-month delay in that response to rainfall. So we picked it up in the dolomites before we picked it up in the other units. So that was also sort of, a nice early warning for the mine to see that there was, this recharge was happening. It ultimately, they all leveled out, but there was a bit of a lag there.
Okay. Thank you, Raymond, for that question. Travis, if you could go in and just click done, because we answered that one live, it will move it from open to answered. And just to point out in the Q&A that there is a little thumb icon there. So our live participants, if you go through, we have a number of questions that are outstanding. If you see any that you really like, you can hit the thumbs up and we'll make sure to pull those ones over some that are less rated. So with that, I will pull up another question here from Jose. So Jose is asking about permeability thresholds for pumping wells. So I've heard some professionals indicate that under a permeability around 10 e to the -5 meters per day, pumping wells do not work. Would this rule of thumb really be correct? So if the panel could discuss any experience with this number or thoughts on this question for Jose, please.
Yeah, 10 e to the -5 meters per day is what? 10 e to the -10 meters per second.
10 meters per second.
Meters per second is 10. That's meters per day. Yeah. So that's a pretty low permeability. That's a pretty low permeability. And so you're not going to get much out of a pumping well, but it depends what you want the pumping well to do. So you're not going to get a whole lot of flow for that. So if you have a mine site where you need to pump, let's say 200-300 liters a second to dewater it, then that permeability is going to give you probably just a couple of liters a second. So that site is not going to be viable. But if you are, for instance, trying to depressurize a clay layer, and you elect that the best way of doing it is a line of closely spaced low flow pumping wells, then getting a liter a second or less may give you what you need. There's several projects I work on where we have lines of pumping wells to depressurize silts and clays, and there's a couple of them where we have also vacuum wells to depressurize silts and clays, and we get very little yield out of them. But if we have the wells close enough spaced, we can do it. So again, so if you've got a large scale dewatering system, that permeability it's not worth putting wells into that. But if you have a system or a need to depressurize a clay and you elect to use closely spaced pumping wells, then maybe you can do it.
Yeah, 10 to the minus 5 centimeters. Sorry, 10 to the minus 5 meters per day is extremely low permeability. It's 10 to the minus 8 centimeters per second, I think.
Yeah.
So that's very well below the threshold where any kind of pumping well is likely to provide any benefit for a site. So a lot of the projects we're involved with in porphyry ore deposit mine dewatering, our rule of thumb is about 10 to the minus 5 centimeters per second is a kind of lower bound threshold, where a general purpose mine dewatering well will provide benefit to the site. And that's just an experience-based number. And the permeability in the ore deposits in the fractured bedrock is strongly controlled by the interconnectedness of the fractures around the well. And so the measured permeability is important, but the sustainability of flow from the well and the amount of time that you can sustain the flow is also very important, and that depends on the interconnectedness and extent of the fracture network. So you can often get a situation where the fractures near a well will initially produce good flow, and you can measure a relatively high permeability value. But once you pump the well for a sustained period, if those fractures are very limited, then the production rate and the effectiveness of the well will quickly decrease, even though you may have measured an initially higher permeability value. So as much as the permeability values themselves, the interconnectedness of the fractures and the extent of the fracture network is also very important for determining the performance of production wells for mine dewatering purposes.
So I was just going to add that if the permeability really is that low on a large scale, that's time to start thinking about hydromechanical coupling.
I thought you might say that, but yes, you're right. I mean, that's below the threshold where you'd expect to see hydromechanical coupling.
Yeah.
I was also following on from what Jeremy was saying. To me, that it's all about connectivity rather than conductivity, and if you can characterize a lithology and give it a single hydraulic conductivity value, then obviously low conductivity is harder to pump from. But if you're drilling a 400-meter deep well through all sorts of different things, it's about how you characterize the flow into that well. How is it coming in? Is it through porous media? Is it coming through one fracture? Is it coming through a fracture system. And so assigning a single hydraulic conductivity to a single borehole, for example, from a single pumping test or something, just doesn't describe how the system works. It's a very crude method for understanding the hydraulics of a system. So you're better to get a much clearer picture on the interaction of the fractures, the connectivity of those fractures. As Jeff said earlier, depending on where you intersect those fractures, if it's high up in the borehole, you may have pump a well for a few weeks or a few months, but once it's desaturated, you're not going to see much water from it. Whereas if the fracture zone is very deep in that well, it'll be a more productive hole and last longer. So I think hydraulic conductivity isn't really the best way to describe the characteristics of a lot of environments.
Yeah, I mean, that's 100%. I mean, I think if you think about what fractured rock is, the rock matrix itself is probably lower than that. It's probably 10 to the minus 10, 10 to the minus 11, 10 to the minus 12 meters per second. So you're never going to pump water out of solid rock, but the fractures may be 10 orders of magnitude higher than that. So you've always got this, in fractured rock, you've always got this massive permeability contrast. And you might have a 500 meter well and 499.9% of that well, 499.9 meters of that well is 10 to the minus 12. And you might have one fracture, which is 10 to the minus 2.
So to keep this conversation sort of in the same area, but to bring up a related question that came in from Mertcan, which I saw also, Travis, you marked this question as one you'd like to address live, but also concerning low hydraulic conductivity materials, but also weak lithologies. So one of the challenges that has been faced in projects involving weak lithologies with low hydraulic conductivities is that dewatering is inefficient and depressurization attempts, for example, drains and boreholes, fail due to the instability of the material. Drilling is also difficult. So given these conditions, if you have any additional conversation topics for Mertcan on how can we collect reliable hydrogeological data in such challenging environments, and what are alternative approaches aside from modifying slope angles can we use to improve slope stability and depressurization?
Yep. So good question. Look, so when you're dealing with a weak rock mass, or anything that's clays and tillites and things, or saprolites, things that are notoriously difficult to drill through, it's the drilling technique that you use that's important, right? You won't get away with your normal DTH percussion, diamond or RC. That's when you got to use techniques like symmetrics or drill and drive, or sometimes sonic drilling, so that you're able to get the hole in and then get the relevant support inside the hole to keep it open. It doesn't have to be large scale. I mean, if it's low hydraulic conductivity, then you can get away with an NQ and HQ diameter borehole with drill and drive, where you install the casing either through the drill string or on the outside if you do drill and drive, and then make sure that the casing is perforated to allow water to then drain in. You can then use that hole to do BMR surveys if you use PVC, because you can do that through the PVC. If you hit enough water, that hole can serve as a drain, or you can get a VWP installed in it. There's actually another question I saw in the Q&A about installing VWPs through casing. So I'll jump to that now, Joel, but the answer is yes, you can do that, as long as the permeability of the casing is higher than the permeability of whatever you're measuring. So as long as water can get in, once you've grouted it up, the VWP can work, and we use that as standard practice, especially in these environments where the holes collapse or it's difficult to drill. When you're drilling inclined especially, this is a nuisance. So the use of casing and then installing VWPs through that is beneficial. The other way around it, if you aren't able to install casing, and this is Simon's bread and butter, is installing VWPs through the drill string. So as you retract the drill string, you can put your VWPs in grout on the way out. Alternative approaches aside from modifying the slope angles. So modifying the slope angle should be the last thing you do, and only if there's some sort of inherent mechanical rock properties that prevent you from going steeper. But the saying is water is the one parameter within the geotech domain that you can control. So it's about the trade-off between steepening or lessening the slope angle versus the spend on depressurization.
Yeah, and
What can you?
I think Travis, weak materials are actually more sensitive. There's more benefit in depressurizing weak materials. Weak materials tend to be more sensitive to water, so it's worth making the effort to do so.
Yep, absolutely.
Yeah, it somewhat depends on the scale of the problem too, right? But looking for the sources of recharge and trying to cut off sources of recharge is also very important. And if it's a high rainfall environment, having really good surface water management on the mine benches and above the crest to try and route surface water flows away from the weak materials is always really important. And if there are other sources of recharge into the slopes, into those weaker rock domains, then identifying what those are and trying to cut them off to minimize the amount of recharge that gets into that weaker material is always very important.
Yeah, I mean, there's a couple of large open pit coal projects that I've been involved in over the years where you've got very low permeability clay in the slopes, and we've gone in with a drain spacing of 5 meters over a large slope just to get it depressurized and to gain 10 degrees on the slope, and on a big pit, 10 degrees will pay for any depressurization.
They could also look at vertical drains too, right? If you can get in the right places and drill through the bottom of the clays or the weaker materials, then vertical drains can be very effective too.
So the other one is looking again at the hydromechanical coupling at Cobre Las Cruces, low hydraulic conductivity and a weak material, marl. They were able to show that the depressurization that resulted from the mining activity and the unloading was all they needed to be able to mine that.
Yeah, and that's written up in one of the appendices in the water book as well.
Mm-hmm.
And maybe that makes me think maybe James or Benjamin, one of you could put a link to what we're talking about when we say the water book to the LOP website. So the question that Travis referred to, I'm going to pull up. So Travis touched on this during his answering, but just to see if any other panelists have any additional comments on this live question. When the goal is to monitor pore pressure using a VWP in a rainfall-prone area where boreholes must be cased to prevent collapse, is it possible to grout the boreholes while the casing with screens remains in place, or is it necessary to remove the casing before grouting? So Travis touched on this a bit. Any additional comments from Travis or the rest of the panel, I guess?
Yeah, Jill, maybe just to add some additional context, we actually deliberately case some boreholes so we can build up sort of a suite of boreholes, say 5 or 10, and then we'll install the VWPs sequentially. So it's sometimes done deliberately, and other times you have to do it because the hole collapses. But I think Simon will definitely have some good input here as well. Not to put you on the spot, Simon.
Yeah, I was going to say this is a Simon question.
Thanks, everyone. It's all about integrity. So what you have to have is there has to be grout that joins the bottom of the VWP sensor, where you've got the filter, and that piece of grout has to have contact with your formation. That's the critical aspect of the VWP install. So in an absolutely ideal world, the hole will stay open, drop the VWP string in on a tremie pipe, and you grout from the bottom up, because that way you know you've flushed all the water out, the grout displaces all the water, and you know that you've got that contact between the filter on the sensor and the adjacent bit of rock. But that's not always possible, and there are many different scenarios that you can install VWPs. Some you have more certainty in the install, and some you have less certainty in the install. Another option, if you can still use a tremie pipe from the bottom up, you can have completely slotted casing all the way down your hole to keep the hole open. And that's just as good, because you've got that connection between the formation and the filter on your sensor through the holes in the casing. In very, very fractured environments where you've got a lot of collapse, we sometimes install where we just slot sections of the screen, but we have to make sure that the VWPs fall into those slotted sections. It's a less reliable method, but sometimes it's the only one that can be done. But what you need to remember is, if you don't manage to get your VWP sensor into the section that's got screen or holes in the casing, your VWP is going to be measuring the pore pressure at the next dominant bit of formation that the grout is in contact with. So it could actually be measuring the pressure head 20 meters above or below the sensor, just wherever that grout can next get out into contact with the formation. So it's just about integrity. It's about taking your time, planning it properly, taking care, and doing the absolute best you can to get that connectivity with the grout between the filter and the formation.
So just quickly, another question, Simon, that I think you may have just sort of answered. Can you confirm or answer this one further? Can the grout affect the pore pressure to be converted to water level by the calibration sheet formula? I'm not exactly sure what that's asking, but maybe just the first part. Can the grout affect the pore pressure?
Not if you use a standard VWP grout mix. You know, the Mickelson is the classic one. So the aim of the grout is twofold. One is to be lower hydraulic conductivity than the formation it is in contact with, and for it to not fracture. It needs to be ductile, so you don't get any preferential flow pathways through it. So as long as you tick those two boxes, then the grout mix won't affect the pore pressure conversion. If your grout mix is higher hydraulic conductivity than the formation it is in contact with, water will obviously preferentially move through your grout rather than the formation. So that will have an impact, but it's generally very rare, as long as you use a standard mix, and unless you're in an incredibly low hydraulic conductivity environment, it's typically very rare. So broadly, I would say no, the grout mix doesn't have an impact.
All right, any other comments on the topic of grouting VWP installation that we may not have covered in those last few questions? Okay, we have let's see, we have 8 outstanding questions in the Q&A, so we'll be getting to those. I don't know what's happening with my camera here. But I will let everyone know we have about 30 minutes left in the webinar right now. So if you want to try to get your question into the queue, now would be a good time to add it into the Q&A. All right, so the next question I will pull up. Let's see what we have here. All right, we'll pull up this one from Jose. Jose, thank you for the question. Panel, please address this question for Jose regarding the execution of drains. In which situations is it more appropriate to drill at a negative angle, and in which situations at a positive angle? So I'll open that up to our expert panel. Thank you.
Okay, I'll take a first stab at
ahead,
that. Drains are always more efficient if you drill them slightly down. The hydraulics is slightly better if you drill them slightly down, because if you drill them slightly down, your drainage point is the collar. If you drill them slightly up, your drainage point is the high point of the drain. So they're more efficient if you drill them down. But I think there's two things to consider. If you are in a formation that has chemistry or where you're likely to get precipitation, if you drill down, then the drain stays saturated. You don't get air into the drain or into the formation, and so the drains tend to clog up less, and so a down angle is good for that. However, if you're in a situation where you've got a large blast damage zone and you have the potential to lose water from the drain into the blast damage zone, then if you drill up, then the drain is not pressurized. So there's less tendency for the water to flow out into the blast damage zone and affect shallow levels of the slope if you drill up. So those are a couple of things to think about, but the bottom line with drains is to think about what you're trying to target. If you're trying to target a structure, think about where it is. If you're trying to target a lithological contact, think about where it is and target the drains accordingly. But within those targets, you've got to think of the things I've just said about the downsides of drilling up and the downsides of drilling down.
Yeah, I agree with that. I think it's all very case by case, and you have to design the drains, including the inclination based on the objective and the target of what you're trying to achieve.
There's also a tendency in some environments to drill drains too deep. I think in the course, if you're trying to achieve some general dewatering and general drainage, then deeper is better. But if you have particular structure or a dilated structure shallow in the slope which you're trying to depressurize, then you just need to reach that structure. And if you drill too deep, you could build water from further back into the slope into that structure.
Yeah.
So not only the position of the target, the depth is also important.
Yep.
We have a couple of related questions I'm just going to bring up related to horizontal drains and the design of implementing drains. So first, we have one that came in from Saurav. I'm sorry if I'm saying people's names wrong. I'm terrible at that. So how do we optimize the placement and design of horizontal drains to manage pore pressure effectively, considering variable hydrogeological conditions and the risk of slope instability? And then another question on what factors do we consider in determining dimensions of horizontal drains? How are optimal dimensions determined, such as horizontal spacing between holes and depth of penetration? So Jeff, you just mentioned a bit about depth of penetration, but if we could add in some information to cover these two questions on dimensions, spacing, and optimization for variable hydrogeology.
So I think one of the things we stress in the course is to certainly do the spacing empirically, and you start up with a trial. So you put in a couple of BWPs and then drill drains around that and measure the response of the BWPs, and that gives you a sense of the spacing you need. And then that trial, you can gradually expand it around the slope based on the empirical responses. So that's typically the best way to do it is to look at responses of VWPs and base your horizontal spacing on that. In terms of weep holes, that's a good question. I mean, weep holes are, we're starting to put those into a lot of situations where we have dilated foliation or dilated structures parallel to the slope. And there's several sites that are involved in there where we've got more conventional horizontal drains, which are 200 meters long, for instance, to depressurize structures deeper into the slope. But in addition to that, we'll put in 5 or 10 meter deep drains just to get water from the blast damage zone. And there's a great example I'm just working on now where we've got piezometers which are about 10 meters behind the slope. And every time they get a rainfall event, those piezometers rise by about 15 to 20 meters. And so now put in a whole pile of, I think, 15 to 20 meter long drains. And so every time now we get rainfall event, the water comes out of those shallow drains and the piezometers only rise by about a meter. So the weep holes it's a good concept just to relieve transient pressures shallow in the slope.
Yeah, you have to be, when you plan a drilling program, you have to think about the potential for unintended consequences of drilling the drains. So, for example, if you drill
Have you lost your
Yep.
Yeah, so what Jeremy's saying is if you drill, you got to think about what may go wrong. And I've been in a couple of situations where we've drains have caused slope failures by bringing shallow water into a budget by bringing drilling too deep and bringing deep water into shallow failure surfaces.
Yeah.
So that's a key thing to think about.
Yeah, thanks, Jeff. The other one is just simply managing the discharge from the drain holes. So we've been involved in projects where the site's done a fantastic job of drilling a program of drains into the slope to target for a geotechnical or a hydrogeological target. And then the flow from those drains has just been allowed to cascade onto the bench where the drains were drilled. And that cascading water, then it ponds up and it recharges back into the benches below. And it can also cause instability. So it's very important to reticulate the drain flow, put the water in a pipe or in a lined ditch or a lined something, and move it away from the bench and the area where the drains are drilled in order to prevent the water from recharging back into the benches below. So there's various different types of unintended negative consequences that can occur with drain drilling. It's really important to think about all of those and plan for them, design them out of the program when the drains are being planned.
Any other comments on this or the first question I flashed, which was from Swarov on also considering risk of slope instability and hydrogeological conditions?
Yeah, I think just to reiterate the point is you have to have piezometers, right? So there's many projects you get involved with and they're drilling drains and the drains produce water, but there's no piezometers to know what they're doing to the pressure. And so the drains are clearly taking water out of the slope, but the effect on the pressure is unknown. So any optimization of the program will involve making sure you've got enough piezometers. And I was just saying to them, we're at the Morenci mine in Arizona at the moment, and we're just saying to the guys yesterday that to start thinking about putting in some more horizontal piezometers. as part of the drain drilling program. I think more and more sites now are putting in piezometers, multi-level piezometers in horizontal holes. And so, particularly where you have slope parallel structure, you can put the piezometers in conjunction with a TDR cable that measures the downhole shear. And so then if you put those in horizontal holes, that gives you great information, not only on the pore pressure, but on any potential deformation behind the slope.
All right. So considering this question from Wilmer, Jeff, just to keep you going on that, would you say you just answered this one, or anything to add for geotechnical criterion for defining the optimal location of sub-horizontal drains in a slope?
So again, I think we hammer the point to make sure your piezometers and make sure your drain holes are focused on where you know, or where you anticipate deformation in the slope to occur. And if you think about a failure surface, the only thing that failure surface sees is the pore pressure actually on the failure surface. So if you've got a failure surface that's let's say 100 meters behind the slope, then if you drill the drains at that failure surface at 100 meters, you're getting maximum benefit of those drains. And if you drill 200 meters, the only thing that the failure surface will see is the removal of pressure at 100 meters at the failure surface. So I think, one of the things we're really trying to stress now is don't put your piezometers too deep. Don't put your drains too deep. Figure out where your instability is or may be occurring, and focus on that area.
All right, thanks. All right, we have about 20 minutes left. Following on a previous question that we talked about, where someone asked about where might you use a VWP versus a standpipe piezo, are there any special recommendations in the case of raw materials and perched levels? From Jonathan.
I think we just talked about that for the past 24 hours. Who's going to have a go at that? There's about 20 people sitting in the room here in Morenci, all with big smiles on their faces. So the problem with raw materials is getting the grout to stay in the hole. So I think we'll answer that question in about 2 months' time once we've done some experiments here. But I think if you can get the grout to stay in, that's the best way to do it. If you can possibly put in some casing to minimize grout loss. Other option would be multi-level standpipe piezometers. Jeremy, you want to have a go at that? Oh, yeah. So I think that's the problem with raw materials is loss into the leach pile or into the dump, and so thicker grout, possibly some lost circulation material, possibly condition the hole with lost circulation material before you put in your piezometer installation. Use fine slotted casing to minimize grout loss, and put in multi-level standpipes if none of those work. But we're doing we're doing some experiments on that right now for Freeport McMoran here at Morenci.
So Jeff, just remind me that the PLS doesn't impact the VWPs in any way?
It doesn't, no. You have to, I mean, I think there's various types of VWPs you can buy. That's probably a Simon question, but we can, there's certainly VWPs which will work in acid.
Mm-hmm. And the grout doesn't have to be anything special either.
You have to think about deterioration of the grout with acid as well. So sulfate resistant materials typically. But I think one of the things we've also been talking about is the LOP project is actually starting to think about this a little more. Maybe triggered on by the recent instabilities in the conventional leach pads in Canada and in Turkey. So I think there'll be some recommendations coming out from the LOP on piezomer installation in leach piles and dump leaches. But preconditioning the hole is a good way to go. Put in lost circulation material during or after drilling, and then put your VWPs in after that.
All right, thank you, Jonathan, for the question.
This is a good question, that. Very topical.
I think we've lost Jeremy.
He's trying to rejoin.
Okay. All right, I'm going to pull up a question that I see, Travis, you have marked as answering live from James. So James's question asks, rather than logging chips or measuring return rates, is it more advantageous to drill with diamond core and measure geotechnical and geophysical parameters during and after drilling, respectively? So Travis, since you marked that one, I'll ask you to start off.
Sure. Thanks, Jill, and good question. Look, I wouldn't say it's more advantageous. It has a place, but it's very difficult to quantify yield on a diamond core hole, or even some smaller diameter RC holes. But where diamond core is very useful is for VWP placement. So if you drill a geotech diamond core hole, you can do your downhole wireline geophysics, your acoustic televiewer, optical televiewer, the various suite of tools, and that can help you plan exactly where you want to put your VWPs. So you get really good resolution downhole as to where you place your VWPs. It can then also give you an indication of where there's structure, at what depth, at what orientation, so that if you move away from that hole, in which direction to move and drill your percussion hole or your large diameter RC hole. So I wouldn't say more advantageous. I would say it should be done with your larger diameter drilling, and ideally done beforehand, right? So this should be the precursor before you go drill your large diameter hole. There would have been some kind of exploration or resource drilling or geotechnical drilling, which is normally done with diamond core. Get your VWP in there, and then drill your larger diameter well, and then use that VWP to do your hydraulic characterization. So I wouldn't say it replaces, but definitely done in parallel in support.
Yeah, I think the main thing with diamond core is there's no airlift data, and so you can't actually hydraulically test the fractures, and you can't actually see what the sustained yield is at the fractures because there's no airlift test. But one thing you can do, and one thing we've again starting to push a little more and to do a little more, is injection tests. You can always inject the core holes. And the thing with injection tests is you just have to think about about the unsaturated zone above the water table, whether you're going to lose fluid into that unsaturated zone. But as I say in the course, you can normally tell if that's happening. So injection tests is something we're doing more and more of. They're easy to do because you can just lower in a transducer and pump in water, so they're easy to do, and so they're a great way to provide hydraulic testing of the formations when you don't have the ability to airlift.
All right. Thank you for that discussion. I'm going to pull up another live question here. Also marked by Travis. So I'll ask Travis for you to address this one first. In the absence of a level logger, will the use of a V-notch be sufficient to determine discharge from Despina?
Yeah. So look, it's pretty difficult to determine discharge or yield with the level logger. But yes, you can do a blow yield using a V-notch weir. That's kind of last resort. If you don't have if you're not doing reverse circulation airlift, you can with a normal detached percussion rig set up your channel with your sandbags, put your V-notch weir in the flow path, and then what's important when using that information is that as soon as you hit water during drilling, that you start measuring your flow rate through your V-notch weir, and you continue to do so until you've reached the end of hole. And then when you develop the hole, so when you basically blow and flush all the drill cuttings, is that you do that and it's going to vary from site to site, but as long as you practically can, right? It's a best sort of proxy for a reverse circulation airlift test. And you make sure that you get sustained flows. So you can't install a level logger when you're using that kind of method. But ideally, what you would have in place is either the pilot hole nearby where you can put a level logger down, or a VWP already. Just be careful when you're using percussion methods that aren't reverse circulation airlift. Just bear in mind that the actual the compressed air being pumped down the hole can affect the reading on the VWP or the water level in the monitoring hole or open standpipe or pilot hole nearby. But yes, we commonly use this. It's the cheapest way to get a blow yield. But you need to use that information carefully, and ideally you only rely on this once you've built up a kind of a repertoire or a register of a number of boreholes, and more than 10, closer to order of 50 or so. Then you can use it reliably. But for greenfields, ideally you want to do reverse circulation airlift or a pump test, aquifer test.
Just to pause back onto the injection testing of diamond holes, just pass on some experience I've just been working on a couple of sites. And for the injection test, what we've started to do is to do a temperature conductivity log of the hole, then run an injection, but make sure that injection test, or try to have that injection test with a different temperature or different electrical conductivity to the formation water, and then run the downhole temperature conductivity log after you've done the test, so you can see which formations the water that you've injected has gone into. So that will enable you to assess where the depth of the productive fractures are. So I've just been actually working on that on a couple of other sites. So it's worked quite well.
So just a quick story about V-notch weirs. I've probably made every mistake that anyone can possibly make. One of them is there's two types of V-notch weirs, 90 degree and 60 degree. Make sure you've got the conversion chart for the V-notch weir you're using, because I've done it wrong.
Yeah, and for those wondering, there's a V-notch weir in my background. Lauren, that's a 90-degree V-notch.
Okay, I think we have time for a couple more questions. Just pulling one up that came in previously through the live Q&A. In the case of permafrost environments, to what extent can you effectively dewater or depressurize pit slopes in permafrost environments? And is it possible to effectively measure the success of those efforts?
Yeah, so there's a lot of experience of this in Red Dog and in the diamond mines in Northwest Territories in Canada, and also at some of the large open pits in Russia. And if you're in the permafrost zone, then obviously you've got more rock strength as well. And so often you don't need to depressurize permafrost because it's inherently stronger because of the ice. And there's a couple of sites I've worked on in Canada and also one in Russia where we've actually put thermistors in behind the wall to measure the freeze back. And so if you expose the pit wall, and particularly for north-facing pit walls in the northern hemisphere, if you expose the pit wall, it actually cools down after you've mined through it. So it makes the rock stronger. Permafrost it does not normally require depressurization, but obviously when you go through the permafrost and you get into the sub-permafrost environment, the risk is, and many operations have had problems with this, is that the sub-permafrost groundwater is often under artesian pressure. It's confined by the permafrost. And so if you don't pre-depressurize it, you can get down with the pit, you come out of the base of the permafrost and you get quite high pressures, and that can create problems with mining and create problems with the slopes. So if that's something, so it's normally quite easy. You just normally need to put in holes to depressurize the sub-permafrost environment. But that's something that always needs to be thought about. What happens when you get below the permafrost, and make sure that you've got enough drains in there so you don't mine into rock that's under excess pressure because of the confining nature of the permafrost.
I think Jeff answered that pretty well. Any other comments from the panel on this question? Okay, coming in from Juan. In your experience on the installation of VWPs in an unsaturated medium, for example, in damage zone to evaluate transient pressures, how real are the negative pressure values and are they relevant to consider?
It depends what they are. So, if you get negative pressures, you can get negative pressures in a clay up to -2, -3, even -4 meters, and they're real. And if you get anything in the unsaturated zone is always under slight negative pressure because it's trying to hold the water into the pore space. So it's inherently under negative pressure, but it's not normally under a lot of negative pressure. So if you're measuring, in a dump leach, for instance, or in a heap leach, you'll often, in an active heap leach, you'll have to measure negative pressures of -2, -3 meters. So they're real. If you're measuring negative pressures of -30 meters, then they're not real. But couple of meters, they're probably real. And they're not relevant to consider. No, I mean, you should never rely on negative pressure unless you've really studied it and you're convinced that it is real. And it's very, very difficult to measure negative pressure below about 1 atmosphere, below 10 meters, because if you think what happens below 10 meters, it's no longer water. It converts to a gas, and so the pore space essentially cavitates, and so very, very difficult to measure negative pressure in a real world situation. And so there's been kind of a lot of work done on that recently, because there are a couple of mines who think they've got strong negative pressures due to hydromechanical coupling. And I think as a group, none of us are very convinced with the data that we see from the tensiometers. So for a real situation in a pit slope where you're trying to measure transient conditions, couple of meters negative pressure is real. You don't need to consider it. It's not relevant. What is relevant is the transient positive pressure.
Yeah, fully agree with Jeff. Just to add, we see it pretty commonly on the tailings dams. You see these -1 meter, -2, up to -3 meter pressures, especially around the walls where you get a bit of drainage. It's very common there. So that is, relevant, but yeah, beyond 3 meters, probably not right.
All right, any other comments for Juan? All right, we have done an amazing job in this webinar. By we, I mean you, the expert panel, on answering an outstanding number of questions. We do have one remaining, but we won't have time to get to that today. Jonathan, I apologize. But I will say that in the water course, there is a final module. I think it's actually called 9 Key Issues, where Jeff overviews some of the main issues that he sees that mining hydrogeologists face in industry today. And so I would invite you to check out that module if you're a student in the course, or reach out to me via email and I can provide you with a little more information. All right, so I want to thank our panel very, very much today for being here, for devoting your time towards furthering the education of everyone involved in the webinar today. I want to thank our participants for all of your great questions and for engaging with us today. And I hope everyone learned something and enjoyed our time in this webinar. Our next one is coming up. I don't have the exact date with me, but it's going to be on monitoring and design reconciliation. It'll be the final webinar in this water series for 2024. So check that out. You can find the date, I think, on the GC's LinkedIn. So thank you, panel. Great having you here today, and everyone have a wonderful day.
Thank you, Jill, and thanks everybody for some good questions. Good discussions.
Agree.
Thanks, everyone. Cheers.
Thanks, everyone. See ya.
Bye.